Skyscrapers are marvels of engineering. These towering giants are not just feats of architectural beauty, but also of human ingenuity and technological advancement. They symbolize progress, ambition, and the relentless pursuit of reaching new heights. They stand tall, defying gravity with their imposing presence. Each skyscraper is a testament to the creativity and determination of the engineers and architects who designed them. But their beauty is more than skin deep. Beneath the sleek glass facades and modern exteriors lies a complex network of structural elements that make these buildings possible. These vertical cities rely on intricate structural systems hidden within. These systems are meticulously planned and executed to ensure the building's integrity and safety. These systems are the backbone of skyscrapers, providing the strength and stability to withstand immense forces. Without them, the skyscrapers we admire would not be able to stand tall and proud. Imagine a skyscraper as a giant human being. Just as our skeleton supports our body, the structural framework supports the skyscraper. The skeleton, hidden beneath the skin and muscles, is what gives us our shape and allows us to stand upright. It is the unseen hero that keeps us stable and strong. Similarly, a skyscraper's structural system is its skeleton, providing support and resisting forces that could topple it over. This hidden framework is what allows skyscrapers to reach for the sky. These forces are not just the weight of the building itself. The structural system must also contend with external forces. Wind, earthquakes, and even the occupancy within the building exert pressures and stresses that the structure must withstand. The dynamic nature of these forces requires a robust and adaptable design. This is where the ingenuity of structural engineering comes into play. Engineers use advanced materials and innovative techniques to create frameworks that can handle these challenges. Vertical structural systems are designed to transfer these loads safely to the ground. The foundation, often unseen, plays a crucial role in distributing the weight and forces. They are the unsung heroes of skyscraper construction, ensuring the safety and stability of these towering structures. Without their expertise, the skyline of our cities would look very different. Not all skyscrapers are created equal. Each one stands as a testament to human ingenuity and architectural prowess, but they vary significantly in their design, height, and structural complexity. Just like trees in a forest, they come in different heights and forms. Some are tall and slender, reaching for the sky, while others are shorter and sturdier, designed to withstand the elements. We can classify skyscrapers based on their height and the structural systems they employ. This classification helps architects and engineers determine the best design and materials for each project. A common classification system categorizes skyscrapers into three groups: high-rise buildings, super-tall buildings, and mega-tall buildings. Each category has its own unique set of challenges and requirements. High-rise buildings typically range from 15 to 30 stories tall. These buildings are common in urban areas and are designed to maximize space while maintaining structural integrity. Super-tall buildings surpass this, reaching heights of over 300 meters. These structures often become iconic landmarks, symbolizing the ambition and technological advancements of their cities. Megatall buildings are the true giants, soaring beyond 600 meters. They push the boundaries of engineering and design, requiring innovative solutions to address the immense forces they face. The choice of structural system depends on a building's height and function. For instance, a high-rise residential building might use a different system than a commercial office tower. A low-rise building might rely on a simple frame structure. These structures are relatively straightforward and cost-effective, suitable for buildings that don't need to reach great heights. However, as buildings climb higher, more robust systems are needed to handle the increasing loads and lateral forces. Engineers must consider wind, seismic activity, and the weight of the building itself. Factors like geographical location also play a role. A skyscraper in a region prone to earthquakes will require different design considerations than one in a more stable area. Buildings in earthquake-prone zones require different structural considerations than those in calmer regions. These might include base isolators, dampers, and other technologies to absorb and dissipate seismic energy. Understanding these factors is crucial for selecting the most efficient and safe structural system for each skyscraper. The right choice ensures not only the building's stability, but also the safety and comfort of its occupants. One of the most common structural systems found in high-rise buildings is the core structural system. Imagine a strong, rigid spine running up the center of the building. That's essentially what a core system is. This central core is typically constructed using reinforced concrete or steel. It houses essential services like elevators, stairwells, and mechanical shafts. But more importantly, it acts as the primary load-bearing element of the building. The core system acts like a giant column, transferring the weight of the building directly to the foundation. It also provides significant resistance to lateral forces like wind loads. Think of it as the central pillar holding up a tent. Examples of buildings using core systems are numerous, from the Empire State Building in New York to the Petronas Towers in Kuala Lumpur. These buildings demonstrate the effectiveness of the core system in providing a strong and stable structure. Section 4. Walls that withstand shear walls and their significance. While core systems provide central support, shear walls act as bracing elements to resist lateral forces. Imagine these walls as shields strategically placed within the building to withstand the pushing and pulling of wind or seismic activity. Shear walls are typically constructed using reinforced concrete and are strategically positioned throughout the building. They are particularly effective in resisting lateral forces that act parallel to their length. Their robust nature helps to minimize building sway and maintain structural integrity. You can find shear walls in various building types, from residential apartments to office towers. They are often combined with other structural systems to provide a comprehensive solution for resisting both vertical and lateral loads. The John Hancock Center in Chicago is a prime example of a building that utilizes shear walls effectively to achieve its impressive height. Section 5. Tubes of power standing tall with tubular systems. As buildings climb higher, the need for even more robust structural systems becomes paramount. The challenge of constructing skyscrapers that can withstand the forces of nature, such as wind and earthquakes, has led engineers to innovate and develop new methods of construction. One of the most significant advancements in this field is the tubular system. This is where tubular systems come into play. These systems have transformed the way we think about building tall structures. Providing both strength and flexibility, they allow architects to design buildings that are not only taller, but also more resilient. Imagine the building's exterior walls as a giant, hollow tube. This tube acts as the main structural element, providing the necessary support to the entire building. The concept is simple, yet incredibly effective. That's the basic concept behind a tubular system. By using this design, engineers can create buildings that are both lightweight and strong. The hollow tube structure allows for the distribution of loads across the entire building, reducing the stress on any single point. By connecting the exterior walls with closely spaced columns and beams, a rigid frame is created that acts like a single, unified structure. This interconnected framework provides additional stability and strength, making it possible to build even taller skyscrapers. This system efficiently distributes loads and resists lateral forces, making it ideal for super tall structures. The ability to withstand lateral forces, such as those caused by wind or seismic activity, is crucial for the safety and longevity of these buildings. There are different types of tubular systems, each with unique characteristics. Some are designed to maximize interior space, while others focus on providing additional strength and stability. The choice of system depends on the specific needs and goals of the project. Framed tube structures, like the World Trade Center towers, use a grid of columns and beams to create the tube. This design allows for large, open floor plans and provides excellent resistance to lateral forces. Tube-in-tube systems, like the Willis Tower, employ an inner core and an outer tube for added strength. This dual-tube design provides even greater stability and allows for the construction of some of the tallest buildings in the world. Tubular systems have revolutionized skyscraper construction, allowing for unprecedented heights and innovative designs. The ability to build taller and more resilient structures has opened up new possibilities for architects and engineers. Their efficiency in resisting lateral loads makes them a popular choice for buildings in areas prone to high winds or seismic activity. The combination of strength, flexibility and innovative design ensures that tubular systems will continue to play a crucial role in the future of skyscraper construction.